Okay, so now we're going to talk about keys versus includes, because sometimes, let me reset my Slack channel. Sometimes when you create a narrow non-clustered index, SQL Server decides not to use it. So why can that happen, and how can you get it to use your index? So continuing on to our journey, we are going to look more at optimization and at whether or not that narrow index can get used, and what we can do to provide a better index for the query that keeps the query from having to go do things like those key lookups. So now what we really want to think about when we're optimizing the query is how much should we cover the query using not only key columns. In that first problem, we were challenged to just create key columns in SQL Server, but we can also, we can do multiple key columns, in which case we have to decide what order is the best for them, and the order really matters. But also we can use these things called included columns to cover the index. Now, an important thing to know is when we're talking about included columns, they only apply to non-clustered indexes, because the clustered, if a table has a clustered index, it is the table itself. When you create a clustered index on a table, you specify one or more key columns by which to order the data itself in the table. And then every other column in the table, in a row store table, every other column is going to be included whether we ask for it or not, right? Because it is the table. When we're creating a non-clustered index, we're creating a whole separate structure that is linked to the original structure. It points to it. But that non-clustered structure is only going to contain the key columns that we specify, the included columns we specify, and then secretly any additional columns it needs to match up rows to the original base table. So when we specify included columns, we only think about them in non-clustered indexes. And this is the way that row store B-tree indexes are structured. Now, this picture here is a non-clustered index, and it's a non-clustered index because we're talking about included columns. The structure is very, very similar for a clustered index. It's just instead of included columns, they are all of the non-key columns, right? Because they're there whether we specify them or not. But looking at a non-clustered index, we've got a root page on the index. There's always this one root page that if we're going to access the data in the index, we can go to this root page and it helps map us to all the other pages. This is arranged in a balanced tree. And what balanced means is that the path to any of these pages down in what's called the leaf of the index, the route to them is going to be the same number of pages no matter what. So if I have an intermediate page over here to access this group, I'm going to have an intermediate page over here. I'm not going to have like 4 levels on half of the index and 2 levels on the other. It's going to be balanced is how it is. Let me hit escape to just clear out my highlighting that I've done. So it's going to be a balanced tree. And then another thing to know is that the key columns we specify, they order the data in every level of the index. So key columns are the only columns that are on these pages. If I specify 3 key columns in an index, they'll be on the root page and any intermediate pages I have. I could have multiple levels of intermediate pages. The included columns that I specify are only going to be in the leaf. They're only going to be in the bottommost level of the index that we have. They just tag along as well. Including things doesn't order them in any way. So like if my key columns, you know, these pages here, they're all ordered by the keys. They're not ordered at all by the includes. And if I change the included columns, it doesn't change the ordering at all. All right, so that's basic structure. Only the key columns impact the page order. So let's look at an example index. And this example index is totally fake. these pages in SQL Server, these pages that I have drawn here, these are all 8 kilobyte pages. So looking at this drawing here, right, I have very little data that I'm describing here. This could all fit on one single 8K page. I don't have more than 8K of data here. And SQL Server is smart enough that if you create an index and there's less than 8K of data that it's indexing, it will just put it all on one page, right? It doesn't have to create the tree structure, but just for illustrative purposes, I've organized this as if we did have 3 pages in this index. So in this imaginary index, just for illustration purposes, we have one root page, we have no intermediate pages at all, and then we just have the leaf, because you don't have to have intermediate pages. You can have just a root and a leaf. So in this case, we have such a small amount of data that all of the data, in fact, is represented on the root page. We have, however, we have a key of first name and row ID. We have included a column of gender. And this is just on some imaginary table, right? So on our root page, we do not have gender on the root page at all. It's an included column. It is not represented here at all. These pages on the root page, this is not really data that we see here. This is pointers to, and in fact, what this has on it, it will have on the actual root page, it will have page numbers on it, because this pointer here is a page number pointer. So it'll basically be like, for Kale and Chris, they're on page number 402. For Chris and Lane, they're on page 403. We have 2 key columns here, first name and row ID. So row ID is on here, but everything is sorted primarily by the first name, right? So everything is sorted by first name. And then if we were to have duplicate first names, it would be sorted then by row ID, but we don't have duplicates. So that secondary key column of row ID, it doesn't really actually play much into the ordering here at all. So let's say we want to run a query and our table is just named X, right? Our table is charmingly named. We want to return the gender where the first name is Lane. Well, we can actually do that pretty well. So we can look here on the root page, and this is just a landmark saying, hey, what page number is Lane on? And it's like, oh, it's on page 403 or whatever, but there's a pointer that says, hey, Lane's over here. So we could seek, pardon me, we could seek straight over there and see that for Lane, hey, gender is male, and we could return that having done a seek that just accesses that one page. What if we want something else though, right? So there's our nice seek. What if we want the first name where the gender is F? Now, gender is not one of our key columns at all, right? Gender is not a key. We do not have it in here whatsoever. SQL Server could choose to not use this index. It doesn't have to. So the optimizer in this case will say, do I have another index that is keyed on gender? Because if I had an index where the first key column was gender, I could go straight to the ones where gender equals F. And if that index also includes the first name, maybe I could get everything I need from that index. So it will see if there's an index that's perfect for it. But let's say there is not another index that's keyed on gender. Let's say that there's no great index where everything is ordered by gender. SQL Server could say, well, this index isn't perfect, but this index does have the first name in it, and it does have the gender in it. Now, nothing's ordered by gender, but I could go down to the leaf of this index, and I could scan every page, and I could put a non-seek predicate on it, right? Gender is not in the key of this index. It is not seekable at all, right? And to be seekable in this case, it would really have to be the first key in the index, right? Because that's my only predicate here. But it's like, oh, well, I could go down here. I could scan every page. And when I scan every page, I could be like, look at every row. Is your gender F? Is your gender F? Okay, it's not, so I don't need you. Go to the next page. Oh, your gender is F. I'll look at you. Hey, you've got the first name on you. So it can do these non-seekable predicates on the included columns as well. And that can be very useful. I mean, why? So you might wonder, why would we want to do this? Because we're having to scan every page in the leaf. Well, SQL Server is smart enough to look around at the different options it has available. if there is no perfect index that's keyed on gender, where it can just seek straight to the rows it wants, it'll look at the available options and be like, I'm going to have to scan somebody who has the smallest amount of pages for me to scan. It could be that the base table, it could be that the table X has 50 columns in it, which makes it take up a lot of space. Well, scanning that thing with 50 columns in it is probably going to take more time than scanning this index that has, 3 columns in it. So this index, if it's physically smaller, it could be less work for it to scan. So it is quite useful that even if the index isn't perfect for the query, SQL Server is smart enough to say, oh, well, if all these imperfect things, what looks like the least work? And that makes our non-clustered indexes be more useful. So we can use these included columns to tailor indexes for queries, and kind of a joke on the name Taylor there, because we will be looking more at our query that's like Taylor. But one of the cool things about these includes is not only we can use them for really 2 purposes. One is like a direct purpose. We can use the includes for the direct purpose of saying, I want this index to perfectly cover a query so that the query doesn't have to go look at the clustered index of the table at all, or it doesn't have to look at any other index in the table at all, because SQL Server actually can use multiple non-clustered indexes if it wants from a single table. But if we make an index perfect for the query, like saying, oh, you don't have to go do any lookups at all, everything you need is in this index and you can seek on the perfect predicates, that index becomes very, very powerful because it's just perfect for that query. And included columns can help make the index perfect for the query. But then there's this sort of non-intentional extra bonus of the included columns. Even if they aren't perfect for the query, SQL Server can find creative ways to use them. And that is really useful because we can't, we are going to create great indexes for our most important queries, but we're going to have a lot of queries that just aren't that important, that we want them to be able to use these as well as they can. And so the included columns can also be useful for that, which is a good thing. So let's see this in action. And this will also play into the question of, hey, why won't SQL Server use a narrow index? So let's say, and in this case, just like SQL Server 2014, SQL Server is going to have questions about these indexes. Let's say we just have 2 single column indexes, right? We do have an index on ref.firstname that's on first name. And we've got an index on ag.firstname by year that's only on first name ID, no included columns here. We've just indexed first name ID. And now our query has changed a little bit. So our query has changed so that instead of babies named Taylor who are girls, it wants all of the babies whose first name is like TA that are girls. So just a slight change to our query. So before we had first name equals Taylor, now we have an inequality predicate of like, saying I just want it to start with TA. So will your query use both of these indexes? Or what is, this is, and I'm gonna go, let's go ahead and spoil it. Actually, your query is not going to use both of these indexes because of the change in the query. Your query is going to be hesitant to use both of these indexes. So your challenge is to say, how can I improve upon these indexes to make SQL Server use both of them? And I'm not telling you which one of them SQL Server isn't going to want to use. That's part of the challenge, is to figure out which of these indexes do I need to improve, and how can I make that index perfect for this query so that it wants to use it. And in explaining this, we'll figure out why it doesn't want to use it as well. So this time you have a template, and let's switch back to the SQL Server and open the problem. So I'm opening for topic 3, I'm opening both the problem and the sample solution. This is the problem, and I'm going to go ahead and create those 2 indexes. These are the indexes where it's not going to want to use them both. And this is the copy of the query. So if you look at the execution plan, you will be able to figure out why it isn't using them. And then the challenge is to create the better index. So let me bring the timer over here. Let's do 4 minutes again. How did you find it? Any guesses on indexes? Oh, there we got a guess. Thank you, Devin. All right, so we've got a guess on first name ID and then gender, and then include name count and report year. All right, so looking through the sample solutions here, and then let me switch back. I think the PDF does actually have some helpful things on this one. Let's take a look here. All right, so I'm going to walk through the PDF a little bit, and then we're going to go and see it directly in Management Studio, because this one is a little bit interesting. So we have changed this from equality to an inequality. And the thing that's changed here is the potential number of rows that could come back, because SQL Server uses some very lightweight things called statistics to help it figure out how many Taylors are there in the database. And now we've changed it to just names that start with TA. And there could be a lot of different names that start with TAs that are girl babies. And some of them may be really, really popular. So we have increased the amount of rows that may potentially come back. Now, SQL Server could use the narrow index that we had. So the index just on first name ID, we could go find, okay, in ag.firstName by year, I'm going to go find all of the rows. Well, so let's step back at the beginning. We're going to first seek using the index on ref first name. So we need to do that because we need to say, okay, for the names that start with TA, what are their first name IDs? So we do need to do that one first there. Then for each row, we get the first name IDs out of there. For each row, we've got our first name IDs coming back into the nested loop. For each row, we are going to seek in the output in the first name ID column. And because it secretly has the clustered index key in there, we are going to output the clustered index key so that we can then later on go find the related rows in the base table. This key lookup is in the base table, and the base table has things like name count that we don't have in the non-clustered index. It will output the name count column, and then we can get it back to the user. So it could use the narrow index. It is possible. But the reason that it may not want to do this is the estimated number of executions. The baby's name TA, there are so many more of them than the baby's name Taylor that if SQL Server were to do this, it's like, oh, I'm going to have to go do this index seek over there like 2,000 times. And then I'm going to have to do the key lookup like 23,000 times because there's a lot of babies whose names start with TA. So it'll think about doing that. It'll consider it as an option, but this is a lot of like, hey, I've got to go do this over and over and over again. And once it starts getting to a point where there's a lot of these, it really doesn't want to do them. So it may actually be more efficient, right? Like instead of having to do all those key lookups, if we don't have a perfect non-clustered index, it may actually do an optimization on a scan. Now there's something cool about this. This looks like, oh, we're having to scan every single row in ag.firstName by year. Right? That's what it looks like. Clustered index scan. Pretty straightforward, right? Well, a scan isn't always the same as another scan. Some scans are more efficient than others. We can see something extra in this scan. So notice this operator up here. Bitmap create. What's that? Well, this bitmap create is a little bit of magic that is helping out this clustered index scan, even though they're on different branches. Like, right, this guy's on the top branch, this guy's on the bottom branch. This is trying to call out graphically that, hey, we're doing a little bit of extra magic here. Now, one thing about this bitmap create, let me go back one. The join operator that SQL Server is choosing here is called a hash match physical join. Now, the logical join in the query, this is just written as, it's an inner join, which in the query, I believe I just have written as join, but it's an inner join. That is the logical operation. The physical operation it's chosen is hash match in this case. Now, we don't always get hash match joins. Before, we were looking at nested loop joins. SQL Server is more likely to choose, and I'm going way back here, SQL Server is more likely to choose these nested loop joins when there's not a lot of rows coming in, when there's not 23,000 rows that it thinks it's going to have to look at it. When it starts getting to the point where it thinks it's going to have to go, hey, 1, 2, 3, 4, up to 23,000, then it's like, oh, I don't want to do this in a loop over and over again. Instead, I might rather do something like a hash join. So in this example, if I have a lot of rows coming in from this table, or maybe even just this table, what a hash match join is it uses space and memory to build tables, and it's going to build one table from this input and one table from this input. It's going to build this one first, and then it's going to have a hash table and a probe table. What it does as part of that hash join is to create a bitmap. So this bitmap here is actually going to be created for this join no matter what. It's calling it out to us. When you see a bitmap create in an execution plan, the optimizer is trying to communicate that it's using the bitmap that it normally would just create for this hash join, that it's using it for something extra. And in this case, if we hover over, and we'll look at this in Management Studio too, I just want it, it's nice for you to have it in your slides. If you hover over this clustered index scan there, you'll see that there is a predicate, not a seek predicate, but there's a predicate on it where it says probe bitmap 1002. And you're like, what? Well, what it's saying here is, okay, we're checking, when we see predicate, that doesn't say seek predicate, we're checking every row, but we're applying a filter to it. In other words, we don't want to send everything along this pipeline. We're filtering it, and we're checking, is the gender F, and is probe bitmap 1002, okay, what is that? Hey, first name ID. So what's happening here? Let's go to the next slide. Well, let's 2 slides, because this is the illustration for bitmap probe. What it's doing is bucketizing this data. And let's actually switch over into Management Studio and look at this bitmap probe there in the solution file. All right, so this is the solution file, good. All right, so I should have already created these 2 single column indexes, good. And the first part of your solution, if we run the query itself, we will see that SQL Server, if I run it with actual plans on, SQL Server has chosen to not use the non-clustered index that's on first name ID. Instead, it's chosen to do the clustered index scan. Here is the bitmap create. And I actually clicked the wrong button here. So notice how I have 0.00 seconds there, and it's like, well, this is 100%. This is because I somehow ran this with live query statistics on. I don't actually want live queries. That's what is going on here. I don't want live query statistics on. So normally I only get this if I do this and run this with live query statistics on. I think it's odd that it's displaying that way. So it's not necessarily a problem. The unusual thing is just that this information here does not usually appear in actual execution plans. And running your query with, this normally shows up if you run your query with like this button, which is live query statistics enabled. There is some overhead to that, and that's why I'm just don't normally run it with that. So in other words, if you run things with live query statistics on, often like in terms of, hey, how long did it take? Or if you're looking at timing or CPU usage, it can be notably inflated. And it's interesting that that's showing up in my plan. Now I'm going to turn this off, and I'm just curious. I'm going to do estimated execution plan, and they aren't showing up there. I don't know if this is an artifact of new. Let's go ahead and just this is a preview version of Management Studio. I'm going to go back to supported version of Management Studio. This is 17.8.1 that I'm running here instead of the new preview 1 of 18. And I kind of did wonder if we were going to find something that would make me move out of that version of Management Studio. And indeed, I think that's a reason enough. So it was fun while it lasted for today's demo, but let's go back into actual supported world. And this is actually how I feel about new versions of Management Studio, whether preview or not, is I test it out for a while against non-production stuff and see if I really like it before I ever point it at anything production, just because I don't know exactly what it's going to do until I'm used to it for a while. So let's go ahead and now open up topic 3 solutions in old Management Studio. And well, if it does that same thing with the operator, that will be very interesting. So, okay, I'm turning on the actual plans. I am in the correct database context. Let's go ahead and look at the query now. Whoa, let's not delete it. There we go. Now I've executed it and I have my plans. And yeah, so now I don't know why it was choosing to show me those special live query statistics in there. This is much more normal. New Management Studio, new fun, right? It is a preview. Okay, so here is my bitmap create. When I hover over bitmap create, it will tell me what it's doing. So hash keys. For the purpose of the way this hash join works is what it's doing is it's taking in the data that it's getting from ref.firstname. And we can see exactly the output list for ref.firstname. It's taking the first name IDs and it wants to shrink them down into these buckets where it basically it's hashing them according to an algorithm. Now we may have collisions, so 2 different first name IDs, the first name ID 1 and the first name, depending on the formula it's being used, the first name ID 1 and the first name ID 1001, they might hash to the same value. But what we're doing is hashing these down into a small set of buckets, and then we're going to take the data from the other index, we're going to hash it into other buckets and then compare them. It will also do a final, if we look at this operator here, it will do a final comparison and make sure like, oh, the non-hashed values have to match as well. It will check for collisions. It will do that. But the hash keys probe here is on first name ID. So one thing that it can do now that it's gone ahead and hashed all these first name IDs, essentially an efficiency it can do looking at this clustered index scan is it can say, hey, I don't want to send every single row across this. So I'm going to go ahead and check while I'm here, are you in what looks like this list of first name IDs that I'm interested in? And because this is an integer value, this word here in row means it can actually pass that word off to the storage engine. So in memory, it can compare these values and only send them back if they match. And that's actually really efficient. And this is why, if we look more on this tooltip, the number of rows read was 36,060. The actual number of rows, what it means by actual number of rows is the number of rows returned out of this operator that has to go along this pipe. It only had to send out 21,000 of them. So it was able to make this clustered index pretty efficient by saying, oh, I'm going to take a shortcut. It's sort of like chutes and ladders. Instead of doing all of the work over here in this join, because I have to process this thing first, and I'm going to create a hashed set of the first name IDs I want, I'm going to go ahead and filter out here before I even send rows into the join so that there's less work to do in the join. It's a complicated world when we're looking at how SQL Server uses indexes, because optimizations like this says, yeah, I am scanning all the data, but I'm able to optimize what I actually send out of this. And that's very important because that minimizes the amount of memory I have to allocate for this hash match join, right? I'm creating these hash tables in memory. So that optimization can really speed up the time that this query takes to execute, even if I am having to scan this. So that in part plays into this. It looks at this and it's like, how many tailors am I going to want to do? And let's start comparing. Does it make the right decision here? So one thing I can do for my query now, I'm going to baseline what it's doing, and I'm adding in an extra measurement here. Before we were just looking at statistics IO. Now I'm adding in statistics time. When I say set statistics time on, and I've done them in one line here as a sort of cheater thing. When I say statistics time, it's going to give me additional information about how much CPU did I use, and that's measured in milliseconds or microseconds, depending on where you're looking, and how much duration did I use. So we're going to look at that for this query. Now this, again, the query is doing a clustered index scan, but it's using that bitmap optimization. So with the clustered index scan, with the bitmap optimization, we are doing, come on, let's center our scan here. We're doing 5,291 logical reads on that index, but our CPU time is 171 milliseconds. Our elapsed time is 317 milliseconds. We are using some parallelism. We can tell from that scan count of 5. So let's run this again and see kind of, yeah, so sometimes we're getting lower counts. This time we were at 100, let's just round it to 100 milliseconds of CPU time here. Looking in our execution plan, we can see, yep, parallel, everybody's parallel here, right? All right, so some of our elapsed time is due to displaying 2,000 rows in Management Studio, by the way. So my rows returned here is 21,313 rows. And you might wonder, well, why is my elapsed time higher than my CPU time? Some of my elapsed time is just the time that it takes Management Studio to get everything displayed in the results pane and to say I'm done. Right, so that is included in my elapsed time. It's time on the client when Management Studio measures this in Statistics IO. So that's one thing to know about why that elapsed time is a little bit longer in this case. So let's look more at CPU time than anything else. We can look at CPU time in the plan itself if we want to. By the way, on SQL Server 2014 SP2 and SP2 and higher, we can say, okay, how much time did this clustered index scan take? Highlighting that operator, looking at my actual time statistics. This clustered index operator was done in row mode. Come on, I want you to zoom it. This was done in row mode, not in batch mode. We'll talk a little bit more about that later. And the CPU time was 109 seconds. So almost all of my CPU time is actually spent doing this clustered index scan. It was done in parallel, so the elapsed time for this is actually smaller because I had multiple, that 109 milliseconds was done across 4 threads that were doing it in parallel, and you can expand that and see, yeah, each of the threads took about 30 milliseconds, 35 milliseconds, somewhere in there. If I go up this in row mode, one thing to know is that oh, that's interesting. This is actually changed. This was not like this before, this might just be me. I'm going to look at this. So one of the things about, let's see if I can find an example here. So actual time, yeah, that's just 1 millisecond there. So notice that my actual elapsed time here is 60 milliseconds. My actual elapsed CPU time is 10. If I go up 1, yeah, my elapsed time is now 3. My CPU time there is 3. My elapsed time is 20. So used to, in row mode, these would show the sum of that item and its children in the branch. It's not doing that anymore. It was just batch mode that would show. So there was an update to this Management Studio as well. I think I did update it. It was just batch mode that would show the time statistics for it without its children. But this is clearly, this parallelism repartition streams actually looks like it might be doing it. I need to look into whether they've updated that or not, because right, this parallelism actual time statistics, lapse time is 56. elapsed time for its child's 35, but the CPU time's gone away, right? It's not showing the child on that branch as well. So I'll have to check into that. In fact, whether they've changed the behavior of how that's output or not. Because used to row mode would show for that zone in the plan, the total for it as well as its children. So I believe that behavior may have just changed in the plans. That's interesting. I'll follow up on that. But we can see for the operators the individual time, and we can see in the plan the CPU time. So the statistics.io stuff has not changed. That's still the same. All right, what if it were to use the narrow index on first name ID only? Why? So it's choosing not to use it and this is a useful thing to be able to do. Whenever I'm like, SQL Server, why aren't you using my index? I can force it. When you use an index hint like this and you say with index, we are not suggesting this. This is called a hint, but what we are saying is you have to use this index. So if I misspell the index, I'm just going to remove that underscore there. If I hint an index that doesn't exist, my query is going to fail. It will not fall back and use a different index. If we hint an index where that exact name doesn't exist, the query will fail because we are directing SQL Server, you have to use this index. But it's useful to be able to do this to say, well, what would the performance be like if it used this index? So if it were to use that narrow index, it would do, notice there's no bitmap lookup here. There's no hash join. It said, oh, if I'm going to use that index, the best way to do it is to do these nested loops. And this is how I could tell, hey, if it was going to use that index, it was going to have to execute this 21,000 times, right? That's how I could figure it out. Looking at our statistics.io, our CPU time here, and I'm running it a few times, our CPU time here, hey, that's not faster than we were before. We were around like 100 milliseconds of CPU time there. We also look at our logical reads. Before we were doing 5,000 logical reads, by using that non-clustered index, we're actually up to 72,000. So using this, it's not faster in terms of CPU time. And in fact, it's less efficient in terms of how much data it's having to access. And that's because it's having to access the ag.firstnamebyyear table twice, once in a non-clustered index, and then once to look up a ton of individual rows in the clustered index. So SQL Server is smart enough to figure out, hey, this actually isn't the most efficient way to run the query, because having this non-clustered index on just first name ID, it doesn't cover the query. And if you're ever like, well, okay, what is it missing? And you're looking at a plan like this where you forced it to use it, we can tell what's missing by looking at, okay, on the key lookup, if I hover over this, what is it outputting from here? What is it going here for? We could also look for predicates. Notice there's no non-seek predicate here, but the output list here is name count. It's going there and like, I've got to have the name count, and I haven't been able to get it anywhere else. So this is why using a narrow index is not always more efficient than doing a scan. What if I were to beat that bitmap probe? So we are going to test the index that Devin has suggested. But first, we are going to look at what SQL Server is suggesting, because yet again, SQL Server is suggesting an index. So notice that we have the green hint here. Once again, there's at least one index suggested, right? There's at least one index suggested. If I go into the properties of the select and I expand missing indexes, this time notice there's no 1 or 2 this time. There's just missing index. So there is only one. It's not like there's a hidden one that I'm not seeing this time. There is only one index suggestion in here. So let's see what SQL Server is suggesting. I'm going to right click and do missing index details. And it is suggesting a non-clustered index on gender include name count. There's something missing from this index. The thing that's missing is our join column of first name ID. SQL Server has not suggested that we put it in this index at all. This is not a very complex query, by the way. Like, it's kind of dumb that it hasn't suggested that the join column should be somewhere in this index because it optimizes queries a lot. But let's go ahead and this is why, like, so there's a lot of hype these days about artificial intelligence and how soon, computers will do everything. They're not there yet. That's what this demo is going to show, is that we still have job security because we can out-index SQL Server. I did give it a nicer name this time. I didn't give it the name of shame, but I am creating an index on what SQL Server suggested, which is gender as the key, include of name count. Let's look at the actual execution plan. It does use the index that SQL Server suggested. And notice that it's not there's no green hint anymore. It is actually satisfied with the index that it requested. It doesn't think we can do any better, right? It was like good enough, right? But it's still using parallelism. See all the little double arrows? It's still saying, oh, I got to use all my cores for this query. It is doing an index seek on the index that we requested. And we might be like, oh, seek is good. Well, seek is not that good in this case, right? We've still got the bitmap operator showing up. We're still doing the hash join. We have to allocate memory to do a hash join. I mean, it's work to allocate that memory, and it ups our query's cost. So we're using multiple, this is a 40 meg table with a 4 meg table. And we're using all of our cores. We're allocating space in TempDB for a hash join, and we're doing a bitmap probe optimization on our predicate here. So it's still able, one cool thing about these bitmap probes is they aren't just for scans. On this case, this index, we are seeking on, the index is keyed on gender. So it is taking advantage of that. And it's like, okay, I'll seek to gender. But it realizes, hey, my estimated number of rows here is huge. Like this is half the table. I mean, it's 20 megs. It's not huge. 20 megs is nothing, but it's enough that I may as well, for all of the half the table that I'm reading, go check, hey, is your first name ID? I'm going to use that bitmap operator and I'm going to look at every single row and be like, does it look like you're one of the first name IDs I'm looking for? And if so, I'll send you out of the operator. If not, I won't send you out of the operator. And it is the storage engine that can do that because it is an integer in this case. So it's able to use the index, it's satisfied with it, but it's actually not that great of an index. Let's measure how well this performs. So looking at the statistics IO for this, data's all in memory, right? I don't have any physical reads or read ahead reads. I don't want to like cheat and make it do more work. But our CPU time, 100 milliseconds, right? That's not better. And we're still doing 2,700 logical reads. That's not that awesome, right? Like, have we actually made this query any faster? Let me run it again. 78 milliseconds there. We did see that earlier, 94 milliseconds. We actually, we got it down. This one, okay, this is slightly faster. We got it down to 61. That's lower than I was able to see before. So it is faster than we started out by like a hair. But essentially what we've done is we're scanning half the table instead of scanning the full table. But yeah, it's still not that great. Still not that great. So, but that was the index SQL Server asked for. Now I am leaving that index there and I'm creating a better index. And this is the index that Devin asked for, except I have a slightly different key column order. So let me switch this to your key column order. So the index that Devin suggested is first name ID and then gender. Now, in this case, first name ID and gender are both equality predicates, right? Because first name ID is in the join. Gender, which I need to spell properly, gender is in the where clause of the query, right? These are both equality comparisons. So the order of them isn't that decisive in terms of changing the query operation, right? Because if we're looking at equalities, we can go straight to one and then look for the secondary order. If either of them were inequalities, like we have on the ref.first name table, then the order would be more like critical in terms of which would have to go first. So this one is created on first name ID first and then gender. And I have done sort of a terrible thing here. I didn't change the name. So now the name describes something different than what's in my index. Not, I mean, like, it seems small, but like later on, somebody may just look at the names and get really confused. If they're dealing with, say, a query that's just like, let's say they were dealing with a query that only cared about gender, where gender equals X. And they're like, why won't this index use it? And secretly the index leads on first name ID. That might not be the coolest thing for me to do. So I apologize to the universe for doing that. It's not production, I swear. So does it use my index? Wait, this plan, it's so simple. How can it be? By creating the perfect index for the query, we no longer have a hash join. We no longer have a bitmap create, which goes with a hash join. We no longer have parallelism. We have two tables with this single nested loop join, and everyone's doing a seek. It's so lovely, right? Like, we have simplified this whole plan down into 4 operators, and one of them is just a select operator, right? It's gorgeous. Our estimated query cost has dropped down to 5.6. The estimated cost to run this is now low enough that it decides not to go parallel, even though it's a shade above 5, which is the default for that. So let's measure the performance for that one. Oh, and by the way, we no longer have to have a memory grant at all. There's nothing, nested loops don't need memory grants. There's no memory grant. The hash join needed a memory grant. Parallelism needs a memory grant. We don't need a memory grant at all. So let's measure the speed of this with statistics.io. We are down to, and 31 milliseconds is basically our average time there. Now, our elapsed time is still a bit high because we are displaying 20,000 rows in Management Studio, which is included in our elapsed time. Our logical reads here, however, is interestingly high. And notice that, so this is the other thing that can play into scan count. So before I tried to word it carefully when I was like, scan count can often mean parallelism, scan count can sometimes mean something else, and we'll look at what that is. So scan count is 2064, logical reads is 6,656. So let's go back into our plan. How many times did we actually run this? We ran this 2,064 times. How many rows did we return? Our actual number of rows is 21,313. Our number of rows, where's our number of rows per execution? It's in here somewhere. What am I missing? That's our estimated number of execution. Oh, it's right there. That's the estimate. I think it just shows in an estimate here. It's like 11.6 rows per execution. Why does that get represented as 2,064 scans? Let's see. I don't think those numbers match, which is an interesting one. We have, oh, there it is. So 2,064 rows are flowing out of ref.firstName into the nested loop. What's my number of executions here? Yeah, there it is, 2,064. So 2,064 executions there, 2,064 scans. Yes, so this is, in this case, showing up as the number of times the nested loop operator had to be executed. But sometimes it just like it really depends on how the table is being accessed as to how it shows up in here, right? Sometimes it shows up as the number of operators you have plus the coordinator thread. Sometimes it shows up as number of time an estimated loop was run. Good times, right? Good times. So this is, in this query, I would say, I mean, the CPU, this is absolutely the best query. The CPU time is the lowest. We have no memory grant that we had to give, and we can confirm that on the properties for this, right? There is no, in memory grant info, I'm going to expand this. Memory grant info, right? Like nada. We did have to, if you dig into the one with the hash join, it has memory grant for the hash join for the parallelism. And this has, even though the logical reads went slightly up, it didn't go up a huge amount. So we do have to measure, like, how is this query good from different points of view. Now, just to recap quickly, like, how does this query cover the index? I'm going to go back to the query and the index. So the covering part is, in the key of the index, we are covering the predicate. So from ag.firstname by year, we are covering first name ID, we are covering gender. We are also covering, this is what prevents the key lookups. We are including report year and name count. That is covering them up here because we are returning them there, right? So we are not only covering the predicates, we are using the includes to add in the columns that we are not putting a filter on them, we are just returning them. And that means, hey, SQL Server, you don't have to go to the base table to look up that column. It's right here in the index for you. It's included in the leaf of the index. You don't have to do any extra work. And that's what the term covering is. Covering is not a term that you'll generally see in the SQL Server documentation. It is a term that's often used in the SQL Server blogging and teaching community. So you will hear people make references to it. If you look for a Books Online article about covering indexes, you may not find one. You will find lots of blog posts on that term covering there though. So to cover or not to cover, that is the question. And this is actually, this question of how many columns should I put in my index and how many includes should I use is actually a really hard one. So in your slides here, it recaps what I just discussed about covering. So filters and order bys. In this query, we didn't have an order by, but if we were, and we will in future problems, if we were ordering by something, we might want to consider that for including in the key of the index because we can pre-order the data along with the order by. Columns in the select list we want to consider for the includes. And I think before I may not have highlighted gender on that slide, gender absolutely. But the thing about gender is we are considering it for the includes as well as for the keys, right? If it's a column can only be a key or an included column. It cannot be both. If we try to put it in both, SQL Server will throw an error and be like, you have to pick. It can be in the keys or it can be in the keys once or the includes once. It cannot be in both. It cannot be twice in either. You can only have a column and an index once. So gender, if we're going to put it in the keys, we would not put it in the includes at that point, but we would want to consider it for both, if that makes sense. The gotchas about included columns is really that they take up space. So for included columns, it's not going to bloat the upper levels of your index because those only contain the keys. They're just sort of tagging along in the index leaf. Sometimes columns end up in the includes just because you have a lot of predicates and there is a limit to the amount of space, the amount of key columns you can put. You cannot, have an unlimited key size. This did get bigger in SQL Server 2016. I think 900 bytes is generally plenty, but because of improvements related to in-memory OLTP, we now have an expanded amount of columns that you can put in your non-clustered index keys, just non-clustered indexes. Note that clustered stayed the same. You can have really giant keys now in recent versions of SQL Server. Generally, if you're gonna need that extra space, I would really question, are you using all of those keys? Because the beauty of indexing is when those are pretty narrow, right? We want to efficiently get places and have relatively small keys. So usually we don't really want the key to be that big, but there's always exceptions to the rule, right? Not every column can be a key. Large object columns can't be keys. And in terms of these limits, by the way, we're going to show these columns that are snuck in. They do not count towards the limit. They're an exception. All right, so what was the best index? What this chart shows is different indexes that I designed and different things I measured in the execution plan about their performance. So Devon's, this is essentially the equivalent to Devon's index right here. Yes, I do have these two keys reversed, but in this case, they are both equality predicates, so it's essentially getting the same performance. For this index, we had the lowest CPU duration, and this duration was measured with a tool that did not display all 20,000 rows. So our durations that we saw were much higher than this because I was using Management Studio that in a mode that displayed all of the results. If we tell it, hey, don't display all the results, the amount goes down. So the winner, and this is one of these examples of which of these queries is the best. We could go by logical reads, right? And I am like, how do I just, there has to be a quick tool to simply erase. We could go by logical reads in terms of whoever has the lowest logical reads is the best. And if we did want to go by logical reads, the SQL Server suggested index actually has really low logical reads. That one that it was still doing parallelism and it was doing a bitmap probe. Now, I actually don't think that's the best index because we were using multiple cores and we were allocating like a 6.5 meg, not a huge memory grant, but we were allocating a memory grant. I think that the best index is actually the one that does slightly more logical reads, but has lower CPU time, a lower degree of parallelism, and no memory grant. But this is the complexity of this. And this is, you know, a small case where you're like, oh, actually, in terms of this, in terms of a real production environment, is 110 CPU milliseconds bad? No, 110 CPU milliseconds is fine. Like, we normally wouldn't worry about this at all. But this comparison scales up, right? Like in the real world, we might be comparing between, you know, 1 second and 160 milliseconds, or 10 seconds and 1 second. This parallels up. But it is often true that we are like, oh, sometimes the fastest query that uses the less resources will do slightly more logical reads, right? So it's not like there isn't, when I'm tuning these, I typically, as I'm tuning, I will look at two things. As I'm tuning, I will look at CPU time and the logical reads. I will keep an eye on duration as well. I'll keep an eye on it because what matters to my customers is actually duration. What matters to me in terms of licensing, right? I license SQL Server by the core, so I pay by the core. So what matters to me is certainly what matters to the customer. That is a big deal, but I also want the cheapest solution that makes the customer happy in terms of licensing over time. So as I tune, I will look at both CPU and logical reads, but I won't look at one as the absolute winner. I want to get my resources for the query down as much as I can while still making the customer happy. So I will also look at things like, does the query have to go parallel? Does it require a large memory grant? Like as I'm going, I'll keep an eye on them. But really what I want to know is, how can I get CPU time the lowest? Looking where the logical reads are can help inform me, how do I get CPU time the lowest? And of course, I want to make sure that as it's going lower, I am getting a low duration for my customer. So I don't tune by just one metric. I tune generally by two metrics, really trying to get the duration down in a cheap way. Clear as mud, right? Clear as mud. So I generally tune by CPU time, and logical reads will help inform me where I'm doing the most work to do that. So takeaways from what we've done so far. Included columns are really important in terms of covering, and essentially covering means creating a larger index so that SQL Server will use it, because it often doesn't want to go do those lookups. It is important to not go crazy on this though. Not going crazy on it. There's two things. If SQL Server isn't using your index, one thing to look at is, okay, am I offering it keys in the right order? Like if SQL Server is not using my index, one reason might just be that I didn't put the key columns in an order that it wants. So I want to double check that, because your key choice really, really matters. Like in our case, the example we were looking at, it didn't matter whether first name ID or gender, their order didn't really matter that much, but it really mattered that both of them were in the key. Because if I only had gender in the key, I could filter out half the data set. If I only had first name ID in the key and I didn't have other stuff in the includes, it would be like, oh, you don't cover me. I don't want to go do all those lookups. So checking our key columns, do we have as many keys as we need for the query? And are they in the right order is really, really important. Of course, in some cases, even if we have all the keys there, it may need included columns to get it to use the index. This is tricky though, because in our example, there weren't that many included columns, but in the real world, you will see little green hints. You will see things in your dynamic management views that are asking for 15 included columns, 20 included columns, 25, 30, 50 included columns, where it's just like, essentially, you'll see these index requests where it's asking for a massive non-clustered index that is a copy of the whole table. And if the table is 5 gigs or 10 gigs or 15 gigs or 100 gigs, right? That's not that unusual anymore. By creating that index, you would be creating the same amount of space in another object. So that's why, like in a small example like this, covering is no big deal. That's not always true, right? So when we have these really big tables, one of the things to think about is just, so, okay, how much are the key columns going to narrow it down to? And the question really is, can I get away with using a narrow index? Can I get away with giving it an imperfect index, or is it just going to not use it? You can guess, but it's really hard to guess because, as we've talked about, different versions of SQL Server will make different choices, right? So that's just really hard. If we really need to be precise, and when do we need to be precise? We need to be precise when it's a really critical system, and we need to make sure that we're using, memory in the most ideal way on the instance. It's not just sort of like, performance, who cares, right? It's critical. In those cases, you want to have a full-size data set to test on. Sometimes this data set may have to have masked values in it. It's not always appropriate. In fact, it's usually not appropriate to just take the production data and throw them into every dev environment that we have. We may need to change some of the data in there. We may need to remove some of the data in there. We may need to mask some of the data in there. Sometimes we just aren't allowed to do it at all, and we may have to generate fake data. And that we want to try to have as similar a distribution as we can, but it's going to be hard because it's not going to have the same distribution. So we want to have similar data. If we can't, sometimes we only have prototype or sample data. If we can't test, will SQL Server use this narrow index? What is our choice? Well, our choice is basically to figure out, okay, I need to cover this because I don't have a way to test. So I need to figure out, okay, how big is the index going to be and is it worth it, right? This can be tough, right? Because we end up creating larger indexes than maybe we need. But if we can't test with realistic data, we don't really have a lot of options there, right? So we just have to kind of weigh what is the lesser evil in terms of it. But if we are able to test, a lot of times we are able to test, will it use this index? Sometimes we can get away with saying, oh, I'm not going to cover the whole thing. I'm just going to give it the keys it needs. And that way I won't weigh my database down. Certain optimizations like those bitmap probes, when you see scans on your indexes, or even when you see seeks on your indexes, if you notice bitmap probes in the plan, look at it and see, is it giving me an extra optimization on this? So those bitmap probes, they are not bad things necessarily. They may see, if you see a bitmap probe, there might be a way that you could tune the indexes to make the query faster. But ask yourself, looking at the query, is it fast enough already? Because that optimization may be making it fast enough that that query isn't important enough to change the indexes on it, right? It might just be using someone else's indexes. All right, so we covered a lot of info in those first two modules. If you got any questions about any of this stuff, the bitmap probes, any of that other stuff, you are welcome to throw them in there into chat.